All right, in this video, what we're going to do is we're just going to collect some vocabulary, and this is vocabulary we'll mostly use for the rest of the class. So let's talk about analytic first. So a complex function, f, is analytic at a point z0 if f is both differentiable at z0 and in a neighborhood of z0. So the picture is this. Suppose you have your point z0, and you know that you can make sense of the derivative there. That's the first check. So f prime of z0 exists. And a neighborhood is an open disk. So not only do you have to be differentiable at z0, you have to be differentiable at all the green points. That's the neighborhood part. So in the last example, we saw this function x plus 4iy, and we saw that this guy is differentiable nowhere. So it follows then that this is not analytic anywhere either. Or analytic nowhere. By contrast, we computed the derivative of the function, I'm forgetting exactly, I think it was 2z squared, no, it was z squared minus 5z. We saw that this was differentiable everywhere. So in particular, it's analytic everywhere. There's no bad points. Now, analytic is often paired with holomorphic, and sometimes they're meant in a synonymous way. So when f is analytic on a domain, that means analytic at every point on the domain throughout a domain D. Then we say f is holomorphic on D. So holomorphic means we can differentiate it everywhere on our domain D. So you might ask, well, what's such an example? So a domain is domain in the complex analytic sense. So this is a open connected subset of C. So I think you can convince yourself that if you looked at the function 1 over z, this is holomorphic on C star, which is C delete 0. For example. So this is a little bit different than the polynomial function z squared minus 5z. So by contrast, f of z is z squared minus 5z is holomorphic on all of C because there's no problems whatsoever. So in this case, in this second case, when the domain of holomorphicity, or however you want to say it, when it's holomorphic everywhere, we generally say that this function is entire. So it's entire. And I think I missed a term. Let's go up real quick. Oh yeah, regular and then singular. So the words regular and holomorphic mean the same thing as far as this class is concerned. And then singular, well, we notice there's a point that's a bad point on this function here, this f of z, and it's a bad point for a couple reasons. Well, first of all, you can't even define f of 0, right? F of 0 is the bad point. We can't even define f of 0. at least not in the way we're used to defining functions. There is a way, but it involves a little bit more geometry. But we can't define f of 0. And so you might ask, well, um, is it uh, is it analytic at z naught? Well, I mean, there's no definition even for f of z naught. But sorry, f of 0. I keep saying z naught. But nevertheless, the point 0 is somehow special. It's like it's the only problem point. So in this case of this example, we would say that 0 is a singular point of f. It's a place where our function fails to be analytic. And we're going to return to singular points later with a slightly better viewpoint, but just want to introduce these now. So singularities of complex functions are actually quite interesting. Okay, so I just wanted to collect that terminology in this video.